talking about delta H enthalpy. Which we said was just equal to our Q at a constant pressure. I don't know if I mentioned this, but your book likes to use this notation. With that P subscript there, it just means you're at constant pressure. Like with bomb calorimetry. Your delta E is equal to your Q at a constant volume, because your bomb calorimeter is always at a constant volume. So, back to enthalpy though. Enthalpy is an extensive property. Does anyone know what that means? It can either be an extensive or an intensive property. What's the difference? Yes. So an extensive property depends on the amount. So if I were to give you this equation, it's balanced, and I give you the delta H associated with it. This means that for 1 mole of C3H8, I am going to give off negative 2,044 kilojoules of heat. Okay, if I were to double that, say 2 moles of C3H8, I would have to also double my value of delta H. So, is this the same example? So that asked you to calculate the heat associated with complete combustion. You should recognize this as a combustion reaction. It's carbon and hydrogen reacting with oxygen to form CO2 and water. But I'm telling you that we're going to start with 13.2 kilograms of propane. Okay, so I have to do a little dimensional analysis. That's it. So to do that, I'm going to need the molar mass of propane. molar mass of propane. All right, so let's start it. We're going to start with our 13.2 kilograms. My molar mass is in grams, so I'm going to go ahead and convert kilograms to gram here. You could have done it before you started, whatever you prefer. Okay, now I'm going to convert it to moles because I know that for 1 mole of C3H8, I'm giving off negative 2,044 kilojoules of heat. So 44.094 grams per 1 mole. So gram cancels, I'm left with moles of propane. Right, now I'm going to use the conversion that 1 mole, and I got this from the balanced equation, gives off negative 2,044 kilojoules of heat. If I want moles to cancel, I'm going to put the 1 mole on bottom. And the negative 2,044 kilojoules on top. Mole cancels. I'll be left with kilojoules. I got a fairly large number, so I put it in scientific notation. I got negative 6.12 times times positive 5 kilojoules of heat. Remember, all that negative means is that it's giving off that heat, not absorbing that heat. Good there. Okay. I think the next thing in your PowerPoint is Hess's law, but I'm going to skip that for just a second, and I'll come back to it. Instead, I want to talk about calculating this delta H here. So if you're following along in the PowerPoint, I've skipped over bond energies and Hess's law. Bond energies, it kind of is the same as what I'm about to talk about. It's just using bond energies. Generally, I don't have y'all do that because I would have to give you so much thermochemical data. I would kill too many trees. All right, so what I want to talk about is what is called the standard enthalpy of formation. So you'll often see this abbreviated as delta H with a degree symbol. That just means we're talking about standard enthalpy of formation, which I'll define. And then that F just means formation. So let me give you a definition for this long word. I'm right here. What do we change when? 4, sorry. Erase. All right, so the standard enthalpy of formation is the enthalpy change for the reaction that forms 1 mole of a pure compound from its constituent elements. So, elements have to be in their standard states, which I'm about to define that word. And the delta HF formation for pure elements in their standard state is 0. For example, and you'll notice that when we're talking about enthalpy, it's often more convenient to use a kilojoule instead of a joule because it's usually a larger number. So for O2 in its standard state, which is a gas, the enthalpy of formation is just 0 kilojoules per 1 mole. So we have defined, chemists have defined a set of standards to measure everybody's enthalpy on, okay? So they follow this standard set of conditions, and over the years, they've compiled a large list of delta H of formations. So there's a huge list in the back of your textbook. But let me talk about what those standards are. Not that you probably care, but I'm going to tell you anyway. All right, so your standard state conditions are you're measuring a pure gas at 1 atmosphere pressure, pure solids and liquids in their most stable form at 1 atmosphere pressure, and a specific temperature. A lot of textbooks and tables use 25 degrees Celsius as the temperature. They just say that's room temperature all across the world. They've obviously not been in this room. Then substances in solution need to be in a concentration of 1 molarity. So there is a slide. I know that you probably can't see it. But here's a small table of some standard enthalpy of formation for some common substances that we'll come across. So we'll never have to calculate the standard enthalpy of formation. This will always be given to you, okay? It's what you do with it next is what you have to calculate. And that is the standard enthalpy of a reaction. So in the last example we did, that combustion reaction, this is how they found that delta H for that whole reaction. Is they took the sum of the delta H of formation for each component. Because there's a delta, it's final minus initial. This would be our equation. Okay, so because there's a delta, I've got to do final minus initial. But final minus initial of what? Well, in a reaction, my products are always my final state. My reactants are always my initial state. So this equation then is the sum of my delta H for my products multiplied by their stoichiometric coefficient minus the sum of the delta H of my reactants, each multiplied by their stoichiometric coefficient. So let me write an example over here. This is in your PowerPoint. I'm not sure of the slide. It's example 9.12. So you technically don't have to write this. Right, so in this example, they pulled all the thermochemical data for you. If they had not, you could have easily looked in Appendix 2B in your textbook and found all of these numbers. The main thing you want to make sure of is when you go to get these numbers, that you pay attention to what state your substance is in. Okay, because if it's in a different state, it has a different enthalpy of formation. All right, so we just need to use this equation with those numbers. That's it. Okay, so I'm going to write it out first, like what numbers I'm going to use, and then we'll plug in just so you can see. So my delta H of reaction is going to be the sum of my products multiplied by their coefficient. So it's going to be 4 times the number for NO2, the enthalpy of NO2, plus 6 times the enthalpy of water. I add those together. And then I subtract the sum of my reactants. So 4 times NH3 plus 5 times NO2. O2, sorry. Okay, so now go fill in your numbers for what I have in parentheses. I'm going to show this step by step just so you get the wrong answer. You'll know why. Right, when you do that, you should get negative 902 kilojoules. I failed to include units, but they're all kilojoules per mole. So these problems are really this simple. These should be give me problems. You just plug in numbers, add and subtract. Yes. Yeah, or you'll be given a table. Okay, so some problems will ask you to like do all this. So you have to find your enthalpy. Then it'll say, well, how much heat is absorbed or released if I were to burn 50 grams of ammonia. Okay, so then you would take what you just solved to figure that out. So let's add that to this problem. Okay, so part B of this could be calculate the heat absorbed or released when 50 grams of NH3 reacts with excess O2. That means I don't have to worry about how much O2 is present. I know it's in excess. So let's do that. Start with 50 grams of NH3. I need to convert it to moles. So to do that, I need its mole mass. Okay. Then I just found that for every 4 moles of NH3, I release 902 kilojoules of heat. Okay, so that's what's next. 4 moles of NH3 give off 902 kilojoules of heat. So now solve. I got negative 662 kilojoules. Because it's negative, it is releasing that heat, not absorbing. Right, so what I'll do is I'm going to go ahead and do like a voiceover PowerPoint just on Hess's Law, just because your pre-lab for next week involves that, and if you have lab on Tuesday, that'll give you time to go ahead and get it done. Then when we come back on Tuesday, I'll just bring us some practice problems that cover all of chapter 9. Like I'll bring us more of these, bring some Hess's Law, some calorimetry, and we'll wrap up chapter 9. Okay, y'all have a good weekend. If I don't see you this afternoon or tomorrow.